Hello everyone, my name is Yihan Cao from Norwegian University of Science and Technology. Today I'm going to introduce you a macro-chain Monte Carlo method named Hamiltonian Monte Carlo. To explain the foundation and the mechanism of Hamiltonian Monte Carlo, it's inevitable to present you some mathematical formulas. But you don't have to completely understand the equations, just to get the general idea underpin them.
This lecture will be going on following the outline you see up here. I'll start with Bayesian inference. Then I'm going to give you a brief introduction on the idea of macro-chain Monte Carlo and one well-known MCMC algorithm named Metropolis Hastings. What follows is a detailed explanation on Hamiltonian Monte Carlo. This section consists of 7 parts in logical order. There are the foundations of HMC, Hamiltonian, generating transitions, leapfrog integrator, and metropolis accept rates. And then an animated example will help you understand how Hamiltonian Monte Carlo works. I will talk about some practical aspects of implementing Hamiltonian Monte Carlo at the end of this section. At last, I will try to summarize the algorithm and the benefits of Hamiltonian Monte Carlo as concluding remarks. Let's first look at Bayesian inference. Bayesian inference is a method of statistical inference in which Bayes' theorem is used to update the probability for hypotheses. Consider a posterior distribution of a parameter theta with a hyperparameter alpha. After taking the observed data x into account, the posterior distribution is determined by Bayes' rule, which forms the heart of Bayesian inference. After applying Bayes' rule to each step of this equation, we end up with this formula. The denominator term doesn't contain any theta dependence, so that the shape of the posterior distribution is only determined by the numerator. The posterior distribution is the distribution of the parameters after taking into account the observed data. The likelihood is the distribution of the observed data conditional on its parameters. The prior distribution is the distribution of parameters theta before any data is observed. So posterior is proportional to likelihood times prior, and it's our target distribution. The exact computation of the posterior distribution is practically infeasible, and some approximation techniques have to be used. For example, we can sample from the product of likelihood and prior distribution to approximate the posterior. One of the methods that can do this is called Monte Carlo macro-chain, in short term MCMC. Before introducing MCMC, I'm going to explain what Monte Carlo means. Monte Carlo simulation is a class of computational algorithms that rely on repeated random sampling to obtain numerical results. Let's look at an example to see how we can use Monte Carlo simulations in order to examine the properties of estimators. We suppose there is a population process where yi is equal to alpha plus beta xi plus some error epsilon, where epsilon is normally distributed with a mean of 0 and a variance of sigma squared. Now we have a sample, which is a dataset from that population, and we use least square estimator to estimate the parameters alpha and beta. Then we take another sample and repeat this for a large number of times n. We will get a range of different values of beta hat for least square estimation. Then, if we plot the frequency of each beta hat, we will get a distribution of these estimates. This sampling distribution should have certain desirable properties for a good estimator. So one of the things that we can check is if the estimator is unbiased by comparing the expectation of beta hat with the true value of beta. We can also check if the estimator is consistent. A consistent estimator means the estimator tends in value to the true population value as the sample size increases towards infinity. Next, I'm going to explain you Markov chain. A Markov chain is a sequence of points in parameter space generated according to certain probabilistic rules. The defining characteristic of a Markov chain is that the probability of transitioning to any particular state is dependent solely on the current state. Repeating this process generates a Markov chain. The idea of Markov chain Monte Carlo is a combination of Monte Carlo simulation and a Markov chain. It is one of the methods that can quantify the typical set of an arbitrary target distribution. The typical set is a neighborhood where only significant contributions to any expectation come from, which is the gray area on this plot. When a Markov transition preserves the posterior target distribution, it concentrates towards the typical set no matter where it is applied. The typical set is illustrated with a kind of arc here. Consequently, the resulting Markov chain will drift into and then across the typical set regardless of its initial state. This provides us a powerful quantification of the typical set from which we can derive accurate expectation estimators from these samples. Let's look at a particular example to understand how MCMC works. We want to know the expectation of a function f of q, and we know the probability density of q is pi q. Then the expectation reduces to integral over the parameter space of q. Computation of this integral is intractable, so we use Markov chain Monte Carlo to stochastically explore the typical set, generating random samples across the region of high probability from which we can construct accurate expectation estimates. Given sufficient time, the history of the Markov chain becomes a convenient quantification of the typical sets. We can estimate the expectation by averaging the target function over this history. As we run the Markov chain longer and longer, it will better explore the typical set, and the Markov chain Monte Carlo estimator will converge to the true expectation. After explaining the basic idea behind MCMC, we next apply it to Bayesian inference. For this purpose, we have to have some data, a statistical model, a function for the likelihood, and a function for the prior distribution, and a sampler. A sampler is basically the way that MCMC is going to explore the parameter space to generate samples. We have multiple choices of the sampler. For example, we have Metropolis Hastings, Gibbs, Hamiltonian Monte Carlo, among many others. Here, I have a diagram showing the process of Bayesian inference with MCMC. So we have data and the parameter theta to construct a statistical model. Then we define a likelihood function from the model, and we have prior distribution for our parameter theta. We feed our likelihood and prior with initial value of theta into the sampler. Then the sampler returns updated value of theta and feed back to the likelihood and prior. This process repeats iteratively many times to obtain sufficient samples for theta. Hopefully, the density distribution of the samples is converged to our target posterior distribution. So next question is how a sampler works. Specifically, we have an initial value for theta as our current sample value. The sampler picks a candidate for the next sample value based on the current sample value. Then, with some probability, the proposal is either accepted or rejected, and the current value is reused in the next iteration. And we repeat this process many times to obtain a sufficient number of samples. The samplers are different from each other essentially in how to make a proposal of theta and how to accept or reject the proposal. For example, The well-known sampler, Metropolis Hastings, proposed a jump that is a stochastic perturbation of the previous sample value. In other words, the proposal is just a random walk. The probability of acceptance is determined by function A of theta prime and theta. Theta is our current sample value, and theta prime is the proposal. Look at the numerator of the second part in the round brackets. The capital P is the target probability density, and the pi is the probability of state transition. By comparing the value of A with a uniform random number, we accept theta primed only if A is larger than the generated random value. For an ideal sampler, the exploration process of MCMC can be divided into three distinct phases. In the first phase, the Markov chain converges towards the typical set from its initial position in parameter space. Well, and the MCMC estimators suffer from strong biases. The second phase begins once the Markov chain finds the typical set and persists through the first sojourn across the typical set. The accuracy of MCMC estimators rapidly improves in this phase. The third phase consists of all subsequent exploration where the Markov chain refines its exploration of the typical set, and the precision of the MCMC estimators improves at a slower rate. However, in reality, the behavior of a sampler might be pathological. For example, as the dimension of the target distribution increases, the volume exterior to the typical set overwhelms the volume interior to the typical set, and almost every random walk metropolis proposal will produce a point on the outside of the typical set. The density of this point is so small that the acceptance probability becomes negligible. In this case, almost all the proposals will be rejected, and the resulting Markov chain will only rarely move. There are other issues might be arised from metropolis sampler, including correlated samples. So we need a better way of exploring the typical set. Now I move on to the topic that I really want to talk about. That is Hamiltonian Monte Carlo. This MCMC method was first proposed by Duane and the others in their landmark paper in 1987. They united the MCMC and molecular dynamics approaches and called the method hybrid Monte Carlo, which was later rephrased as Hamiltonian Monte Carlo by the other literature. The statistical applications of HMC began with the use of it for neural network models in the published paper from Neil in 1996. Hamiltonian Monte Carlo can be viewed as a variant of Metropolis Hastings algorithm. To prepare for this lecture, I relied on a lot of the contents, in particular these two papers. If you have any interest in the technical details on HMC, I would recommend you the latter one, which I think is more understandable. To help us understand the Hamiltonian Monte Carlo method, we consider the MCMC from a geometric perspective. Imagine that we need to exploit information about the geometry of the typical set. Specifically, we need jumps or transitions that can follow these black arrows coherently gliding through the typical set, as shown with the green curve. Hamiltonian Monte Carlo is the unique procedure for automatically generating this coherent exploration. In this section, I'm going to talk more about the intuition of Hamiltonian and then discuss the procedure of the method more formally, ending with an animated example and practical information on the implementations of Hamiltonian Monte Carlo. Hamiltonian dynamics has a physical interpretation that can provide useful intuitions. The exploration of a probabilistic system is mathematically equivalent to the exploration of a physical system. For example, we have a typical set, which is the space around a planet through which we want a satellite to orbit. This analogous physical system suffers from the same pathologies as the motivating probabilistic system. In particular, a satellite at rest will fall under the planet's gravity and crash into the surface of the planet. Without enough momentum to balance against the gravitational attraction of the planet, a satellite will still crash into the planet. On the other hand, if the satellite is given too much momentum, then the gravitational attraction will be too weak to capture the satellite in a stable orbit. The satellite will instead fly away. When we introduce exactly the right amount of momentum to the physical system, the subsequent evolution of the system will then trace out orbital trajectories. In order to mimic the satellite's behavior in our probabilistic system, we need to introduce auxiliary momentum parameters m, and thus expand our d-dimensional parameter space theta into a 2D-dimensional phase space for theta and m. In Hamiltonian Monte Carlo, imagine that the energy of a satellite is the sum of gravitational potential energy V, which depends only on the position of the satellite theta, and the kinetic energy, that is the function of momentum m. Then we define a joint distribution for our parameters theta and the momentum parameters m, which is called the canonical density, and relate it to the Hamiltonian. Because of the decomposition of the Hamiltonian, the joint density decomposes into two terms. One is minus log of probability density of theta, and another one is the minus log of probability density of m conditional on theta. We find that these two terms are corresponding to the potential energy and the kinetic energy. And the potential energy is only determined by the target distribution, but the kinetic energy is unconstrained and must be specified by the implementation, which is the first substantial degree of freedom in the Hamiltonian Monte Carlo method. That's the choice of a kinetic energy function. One choice of the kinetic energy is given by momentum squared divided by 2 times its mass, which exactly corresponds to the half mv squared we learned at high school. The total kinetic is the sum of the kinetic of a fictitious particle in all its d dimensions. That's what the subscript I here corresponds to. I'm going to assume d equals to 1 and mass is equal to 1 just to simplify the following explanation. In this simplest case, k of m is just equal to the half of m squared. Thus, the probability density P of m can be recognized as a standard normal probability density. Remember that our canonical density is proportional to this, and what turns out is the canonical density is proportional to the product of our unnormalized posterior and a standard normal PDF in the case where we have chosen the simplest implementation of the kinetic energy. So far, we have done a lot of sort of mathematical manipulation. So what's the point of this? In a second, we will see the marginal distribution of P of theta and m is actually our target posterior distribution. So if we integrate P of theta and m with respect to m in order to marginalize the joint density, it turns out we only need to integrate the standard normal density, and the first part can be moved out of the integral with a normalizing constant c. So the marginal probability density reduces to our target density. In practice, we don't have to calculate the integral. What we do is we sample from the joint distribution of theta and m, and then throw away all of our m samples, so that the marginal samples for theta will be the samples from the target posterior distribution. So now the key question comes: how we can generate proposals or samples for theta and m. The Hamiltonian Monte Carlo makes use of these two equations to describe how theta and m change over time. To be specific, the change of m over time is determined by the partial derivative of the Hamiltonian with respect to theta, and the change of theta over time is the partial derivative of the Hamiltonian with respect to m. I'm going to make an example. Consider a Hamiltonian function where the potential energy is the half of theta squared and the kinetic energy is the half of m squared. So the change of m over time turns out to be minus theta, and the change of theta over time equals to m. Then the solutions for theta and m have the form you see up here, for some constants r and a. For any time interval of duration s, these two equations define exact trajectory for theta and m from the state at any time t to the state at time t plus s. And we can obtain the samples along the exact trajectory for theta and m. However, in practice, obtaining analytical solutions for theta t and mt is extremely difficult. Consequently, it is almost impossible to simulate the true trajectory in the parameter space of theta and m. So what we should do? For computer implementation, what we have to do is we approximate Hamiltonian equations by discretizing time using some small step size epsilon. One method of approximating the true trajectory is called leapfrog algorithm. The idea is, starting with the state at time t, we iteratively compute approximately the state at time t plus epsilon, t plus 2 epsilon, t plus 3 epsilon, and so on. For each time duration epsilon, we start with a half step for the momentum variable m, then do a full step for the precision variable theta using the new value of the momentum variable, and finally do another half step for the momentum variable using the new value for theta. Note that we only keep samples at the start and end of each iteration, which consists of L steps, and in this case, L is equal to 3. By repeating the process iteratively, we are able to approximate the exact trajectory. Thus, it is one of so-called symplectic integrators. We should remember that leapfrog integrator alternates half-step updates of the momentum and full-step updates of the precision. Since the leapfrog method discretizes time to approximate the true trajectory, it unavoidably creates local errors due to the discretization. Local error is the error from time t to t plus epsilon. The local errors add up and form the global error, which is the error accumulated for some time interval s. But a nice property of leapfrog algorithm is that their approximation error cannot add up coherently to pull the numerical trajectory away from the exact trajectory, which is the red curve on the figure. However, instead, the numerical trajectory oscillates around the true trajectory, which is the green arrows on the figure, even as we use very small step size epsilon. If the leapfrog integrator were perfect numerically, there would no need to do any more randomization per transition than generating a random momentum m. But in practice, what has to be done to account for numerical errors during integration is to apply a metropolis acceptance step, just as we do with a random walk proposal. We have in the beginning of this lecture introduced the metropolis acceptor rule. Here, we only extend the rule from the parameter theta to including the parameter m. So the acceptor probability R is the ratio of the canonic density at theta primed and m primed to the canonic density at theta and m times the ratio of transition probability from the proposal to current state to the transition probability from current state to the proposal. But one noteworthy thing is Hamiltonian trajectories and their numerical approximations are deterministic and non-reversible. What does that mean? It means the probability of the state transitioning from theta m to proposal theta primed m primed is equal to 1. So the denominator up here is equal to 1, but it can never go backwards in time. So the transition probability as the numerator here is always equal to 0. Consequently, Metropolis Hastings proposals are always rejected. So what we should do to make the Metropolis acceptance rate valid? The solution is actually very simple. We negate m primed, so that instead of evaluating theta primed, m primed, we evaluate a proposal theta primed minus m primed. Since the leapfrog method is symmetry, the transition probability from theta primed minus m primed to theta m is actually equal to 1. So the numerator here is equal to 1. The denominator is also equal to 1 since theta primed minus m primed is obtained only by negating m primed. So in the ratio equation, the second part vanishes and the ratio reduces to a simpler form. The rest of the Metropolis accept step is to compare the value of R to a uniform random number U. If R is larger than U, we keep the proposal as theta primed minus m primed. Otherwise, we stay at the current state. To summarize the sampling process, look at these two diagrams we used to introduce the leapfrog method. At the end of each iteration, we have a proposal. We flip the sign of m in the proposal and then evaluate the proposal with the Metropolis accept rate. If we accept it, we save the sample theta minus m and use it as our current state. Then, at the beginning of next iteration, we use theta t plus 3 epsilon as our current position and draw a fresh value for m. Then we repeat the leapfrog algorithm and end up this iteration with another proposal. If this proposal is rejected, we save the previous sample in memory again, which means this sample is counted twice for posterior analysis. And we repeat this process many iterations. To summarize, the Hamiltonian Monte Carlo method makes a proposal by computing a trajectory according to Hamiltonian dynamics implemented with the leapfrog method. Specifically, it starts with an initial value for theta, either specified by user or generated randomly, and an initial value for m sampled from a pre-specified probability density function. Then the leapfrog integrator updates the values of theta and m with discretization time epsilon and the number of steps L, according to the Hamiltonian dynamics. Then the proposal in M is negated and is decided to be either accepted or rejected with the Metropolis acceptance ratio. Then we draw a fresh value for M and repeat step 2 and 3 for many iterations. At the end of the exploration process, we throw away all the samples for M, and the rest are the posterior samples that we want. Now let's look at an example. We were to simulate samples from a target posterior distribution of theta that has a kind of bimodal form that looks something like this. So there, theta is one-dimensioned. Then I'm going to show you the path of a fictitious particle in the canonical density space of theta and m. To get the joint space, we have to introduce a momentum variable m. So we multiply the posterior of theta by a standard normal density. And then I get a two-dimensional distribution, which is shown here with a 3D representation. The canonical probability density looks like two adjacent mountains. So we have our position theta on one axis and the momentum along another axis. Another way of representing the canonical density is shown here on the right, which is just a contour plot. Next, I'm going to show you the path of our particle over time on this contour plot with a short animation. I'm starting with a fictitious particle that locates at halfway between these two modes. Now I'm going to run the sampling process over time. We can see a green path here, which is kind of arc-shaped. The green color indicates that we ultimately end up accepting this proposal. The particle is moving step by step because we are solving the path over time with the leapfrog integrator. After we continue to solve for this path in both momentum and position space for all the green steps, we get to the position where is the end of the first iteration. I'm going backwards a bit. So what we do next is we flip the sign of momentum. That's why we jump up to the point up here. Given our metropolis accept rate, it turns out we actually accept this proposal. So this forms the second sample from our joint distribution. Then our point jumps down, as you can see here, because we are sampling a fresh value for m. Then we continue with the second iteration. If we didn't sample a fresh value for m, the particle would get stuck in the neighborhood of the current state. We can continue this process, so in each iteration of the algorithm, we sample a new value of m. If we think of the solid dark contour lines as energy levels, we can see the particle changes energy level substantially by flipping the sign of m. In the end of the animation, you will see that we will have the rejected proposal, the path of which is shown in orange. What you can see here is that we are starting to build up a range of samples, which if you look in the theta dimension, we start to get a lot of samples towards the left mode. If we were to run the iterations many times, which I will show you soon, we eventually obtain the samples at the joint space. If we throw the m samples away, we end up with the samples for theta, and the distribution of them converges to the desired posterior distribution. By jumping m values up and down, we are actually exploring the joint space very efficiently, since we are proposing reasonable values of energy, which encompasses the entire range of energy. I'm speeding up the sampling process a bit, so you will see the orange path later on. Now I'm going to run the process of Hamiltonian Monte Carlo on this particular example for longer. We can see here above the contour plot, there is a dashed black line which is our desired posterior distribution, and to the right-hand side we have also the dashed black line representing the desired marginal distribution for our momentum m. Now I'm starting the sampling process far away from the joint density mode. What I'm going to show next is not the entire path of the fictitious particle, but only the accepted states at the end of each iteration. So you will not see the momentum variable flipping sign over the trajectory. As I run the sampler longer and longer, we can see that we are sampling a lot from the mode at our right-hand side. After we transition to tens of thousands of samples, the marginal distribution of samples for the right mode and the distribution for m look close to the desired distributions. Then we continue the sampling process a bit longer. We can see that the particle has transitioned to the typical set for the left mode. After 20,000 samples, we have got very close to the marginal posterior distribution. For the momentum distribution, we have converged pretty closely to the desired normal distribution. The example I showed you is actually not an easy problem due to the dual modes. And in practice, there are almost no Hamiltonian transitions that are immediately applicable. We have to carefully tune the parameters in the HMC to achieve a good performance. The first substantial degree of freedom is the choice of the conditional probability distribution over the momentum, or equivalently, the choice of a kinetic energy function. The most often used density distribution over the momentum is called Euclidean Gaussian. The Euclidean matrix Q, which is the variance-covariance matrix of Gaussian distribution, is known as the mass matrix. The d momentum variables are usually independent, so that the variance-covariance matrix Q is diagonal. A Riemannian structure allows us to construct a Gaussian distribution over the momentum, whose covariance depends on our current position in parameter space. If the matrix sigma is well chosen, then this modification can significantly improve the performance of the Hamiltonian transition empirically. In theory, we are not limited to Gaussian distributions over the momentum, but empirically, non-Gaussian kinetic energies tend to perform poorly, especially in high-dimensional problems. Secondly, the parameters in leapfrog integrator, the step size epsilon, and the number of steps in each iteration L must be tuned to optimize the performance of HMC. In practice, sampling efficiency is actually highly sensitive to these tuning parameters. If step size is too large, the leapfrog integrator will be inaccurate and too many proposals will be rejected. Smaller sample size yield more accurate numerical trajectories, but at the expense of many more integrator steps. Similarly, if L is too small, the trajectory traced out in each iteration will be too short and the sampling will devolve to a random walk. If L is too large, the algorithm will do too much work on each iteration, which might even end near its starting point. In practice, epsilon and L can be chosen randomly from a selection of values advised by preliminary runs. At last, instead of leapfrog integrator, there are other integrators available, such as Euler's method and modified Euler's method, but they turn out to be less accurate in approximating the true trajectory. I'm now going to introduce you briefly a platform for implementing HMC for Bayesian inference. It is called STAN. It's a probabilistic programming language for statistical inference written in C++. It implements gradient-based MCMC, including HMC algorithms. And the MCMC algorithms employed by STAN include Hamiltonian Monte Carlo and the no U-turn sampler, which is a variant of HMC and the default MCMC engine in STAN. STAN allows the step size to be adapted or set explicitly. It's able to automatically optimize epsilon to match an acceptance rate target. If you choose to use the no U-turn sampler, it can dynamically adapt the number of leapfrog steps L by choosing a criterion for determining when a trajectory has grown long enough. It is also able to estimate Q based on warm-up sample iterations. STAN can be accessed through several interfaces. For example, in R, the library is called RSTAN. In Python, it's PySTAN. And in MATLAB, just MATLAB STAN. In summary, Hamiltonian Monte Carlo is a variant of the Metropolis-Hastings algorithm, and the way in which it differs from standard Metropolis-Hastings is by using a physical analogy to generate proposals for parameters in the model. And the physical analogy that helps us is by introducing momentum variables to expand the parameter space so that our fictitious particle is able to trace out a coherent trajectory through the typical set that efficiently moves us far from the initial point to new unexplored regions of the typical set as quickly as possible. The leapfrog integrator is used to simulate numerical trajectories that approximate the true trajectories. And a Metropolis-Hastings accepted step is implemented to correct the approximation errors created by leapfrog integrator. After throwing away the M samples, the rest are the posterior samples that we want. HMC yields not only better computational efficiency than other Markov chain Monte Carlo algorithms, but also stronger guarantees on the validity of the resulting estimators. Consequently, Hamiltonian Monte Carlo is uniquely suited to dealing with the most challenging problems at the frontiers of applied statistics. That's all I want to talk about Hamiltonian Monte Carlo. Thank you for listening.